Hello everyone, my name is Geek37 and I'm doing a video series on the heptagonal triangle. The heptagonal triangle is the key scalene triangle in the regular heptagon. It is done in such a way that the angles are pi over 7, 2 pi over 7, and 4 pi over 7. Now I'm in my GeoGebra program here. As you can see, this triangle is drawn out. ACG is the heptagonal triangle. And pi over 7 is equivalent to roughly 25.7 degrees. 2 pi over 7 is equivalent to roughly 51.4 degrees. And 4 pi over 7 is roughly equivalent to 102.9 degrees. Now, as you noticed, this scalene obtuse triangle goes from pi over 7 to 4 pi over 7, and the middle angle is 2 pi over 7. The measurements there are all in radians. This is the only scalene triangle that exhibits a doubling of the three angles from 1 to 2 to 4. And this triangle has a lot of interesting properties. Now, what I'm going to do is we'll start with the Wikipedia article on it. There's a lot of interesting properties that I will prove in future videos, especially relations of distances from the sides, as you can see here going down. I'm also going to prove some altitude properties, as you can see here, internal angle bisector properties. The only one that is different is this omega, or this WA, as you can see on your screen here, is B plus C. That's an external angle bisector. I will do a video on that. I will also do one on the area formula relating to R, which is the triangle's circumradius, which is the radius going from the outside of the circle to the any of the vertices, because since it's an obtuse triangle, the circumradius will be outside of it. I will prove these relationships here, that with a squared b squared plus c squared equals 7r squared, for example. I will also do a couple of these where they have the reciprocals of their squares and their fourths. I'm also going to prove a bunch of different trigonometric properties, as you can see here. Now the ones below this point with the cotangent squared A, cotangent squared B, and cotangent squared C. A, B, and C, those capital letters, are the angles in order from smallest to largest: pi over 7 radians, 2 pi over 7 radians, 4 pi over 7 radians. These are actually quite difficult to prove. I've been able to prove a couple of them. I'll try and make videos on them, but I have been unable thus far to prove all of these, so these might be mysteries until I eventually figure them out. These sign relationships going down here, I know the first one I can prove quite easily, and the second one can be proven as well, maybe the third one, but as you can see, the powers get bigger and they're a little bit more difficult to prove. So I probably won't touch on all of those. There's a lot of more interesting properties here. You can see in this page, you've got the Ramanujan type identities named after Srinivasa Ramanujan, one of the greatest mathematicians from India and of the 20th century. I don't know if I'd be able to prove these on paper if I could try. There's also another article that you can find if you type in heptagonal triangle into a search engine. The first two entries that usually pop up are the Wikipedia article, and then you get one from mathworld.wolfram.com or Wolf from Mathworld. Probably the preeminent mathematical encyclopedia before Wikipedia came on the stage. There's a number of properties listed here. The interesting thing is this triangle, properties about it were published in Mathematics magazine in 1973 by two authors named Bankoff and Garfunkel. It is quite an interesting article if you can get your hands on it. All of the stuff comes out of there. The Brocard angle of cotangent omega equals pi over 7. That can be easily shown with going down here to where we get cotangent A plus cotangent B plus cotangent C equals pi over 7. To get the Brocard angles of any triangle, it is the sum of the cotangents of the three angles of the triangle. That might be a proof I can do in a separate video as I bring my channel more to life. It shows some other interesting geometry here that I might get around to proving if and when I can, but as you can see, there's a long list of also of trigonometric properties that I intend to prove. And this one here, this is one of my favorites, sine A plus sine B plus sine C equals half cotangent of pi over 14. That is quite an interesting proof there. So in summary, I just wanted to tell you that I'm going to be doing a series of videos on the heptagonal triangle, and those by extension are properties of the regular heptagon itself. It's true for pretty much any placement of the triangle in the regular heptagon. As you can see here, FDG is another example of that. You can also slide one over to here, DFC, as you can see there. So whenever I do a proof of something from the heptagonal triangle, it'll also be a proof of an identity from the regular heptagon itself. If I do wind up proving something that's not exactly related to the heptagonal triangle, but to the regular heptagon itself, I will probably do that as a separate video apart from this playlist. I hope me rebooting this series will bring interest to a mathematical topic that I've always found fascinating and that the wider world deserves to know about. All right, this is Geek 37 signing off.